Okay, good morning, everyone. I'd like to start day one with a few logistical announcements for the benefit of those of you who couldn't join us yesterday. My name is Rachel Street, and I am PI of the TARM Toolkit project, and I have the great pleasure of working with a really excellent team of software engineers and scientists who are both putting the original TARM Toolkit together and also running this workshop and the development program. All of us will be around all of the week, so feel free to come and ask us questions at any time. The overall format of the workshop is going to be mostly in the mornings. It's going to be plenary sessions with a set of invited speakers designed to illustrate all aspects of the whole follow-up ecosystem. This is going to be supplemented with a few group discussions where we would like to hear from all of you. So we will be splitting into different breakout sessions where you will get to influence what we discuss and the impact that we have and the content of the summary talks. And lastly, we'll have a sequence of hands-on tutorials where you'll get a chance to really use the toolkit in great depth and really understand how to put a TOM together. So the venue is as follows, if you haven't had a chance to look around the building already. We're right now in the main auditorium, and you had breakfast outside in the foyer. The hands-on breakout sessions will be in the Hale Library, the main conference room, and the garden level conference room, and all of those sessions will be identical, so you can join anyone at any time. Please don't leave any of your stuff in any of the rooms unattended. We do have limited parking available. It's on this parking lot on the side here. And you're welcome to use the garden for lunch or whatever. You'll find information on local restaurants is on the website. Of course, this is the important information you need to know, so feel free to take a picture of that slide if you want. If not, you'll find the information is up here on the whiteboard at the same. Please note it is case sensitive. So you already discovered breakfast. That will be served every day from 8 a.m. We'll also have refreshments at morning and afternoon coffee. And for lunch and dinner, you're on your own, but there's plenty of food and restaurants, easy walking distance. And we can arrange to have food delivered if you let us know. We have a meeting code of conduct. It's very similar to the LSST code of conduct. And it's not complicated. It's basically be civil and professional at all times to make this a really productive meeting. If you have any questions or concerns at any time, please contact myself or Sandy, who's sitting right at the back there. Social media is an essential element of every meeting these days. We have a Twitter feed. Feel free to use it. And do keep an eye on the Slack channel that we set up for the meeting, because that's the primary channel where we will make announcements and give information. For those of you who are speaking, you should have received instructions already for uploading your talks to the shared folder. This Podium Mac can support all common formats for your talks. If you look in that folder, you'll also find a shared Google document, which is intended to capture any ideas or suggestions that you have. They don't have to be fully thought out, but we would really like your feedback both on the workshop and also on the toolkit itself. So anything that is going through your mind that you think would be an interesting thing to develop or collaborate on, feel free to make a note of it in the document given in that folder. We are recording the plenary sessions. Thanks to LSSTC, have provided a BlueJeans channel for this purpose. The meeting ID, if you at some point want to join us by the online system, is given there. But I would ask that if you ask any questions, please don't use the chat screen in the BlueJeans channel because it's not easy for us to monitor. Instead, if you could use the Slack channel for that purpose, that would be great. We have an open data policy by default, and I would like to make all of the presentations and materials for this workshop available online after the meeting. If I understand that some people have sensitive content in their slide, if you do, please let me know, and of course I'll respect your wishes. And you should mark any content that is sensitive with the anti-tweet symbol here. And conversely, everybody who is watching these slides, if you see that symbol, I don't want to see it on Twitter. We will be taking some workshop photos, and if you prefer not to be photographed, please let us know. That's perfectly fine. We will be taking a group photo today at noon, and the Carnegie have arranged to turn on the prism at the Solar Observatory at Mount Wilson and shine it as a spotlight into the parking lot. So we will be doing that at noon today. So please join us if you can. And that's it for announcements. So at this point, I'd like to introduce David Coulter, who's kindly agreed to chair the session this morning. David.
Hi, everyone. My name is Dave Coulter. I'm a fourth-year graduate student at UC Santa Cruz, working in Ryan Foley's group, but I do mostly gravitational wave search and follow-up, so I'm definitely in the trenches with you all for O3, and I'm super happy to be here and be involved in this workshop and introduce our speakers. So up first, we have Chris Burns, who's going to give us a welcome and a brief history of the Carnegie Observatories.
Okay, hello everyone. Welcome to Carnegie. John Mulcahy sends his regrets. He was going to initially give this welcome and a little bit of history, but he was called away on other business, so I will be taking his place. So I'm going to say the subtitle here is that Carnegie Observatories is the birthplace of astrophysics, and I will back that up. This is what we often tell our visitors. So a little history. This is Mount Wilson Observatory. If you haven't been, especially for you local folks, they have tours on Saturdays and Sundays that are actually quite in-depth. So it used to be that you'd only go up and walk around on the grounds, but now they'll take you into the telescopes. They'll show you all the workings and everything like that. So if you haven't been up there recently, I encourage you to go up because the tour guides are quite knowledgeable, and it's quite a great way to spend your afternoon. So you probably heard the name Carnegie all over, and it's Carnegie, Scottish, okay, or Carnegie. There's lots of Carnegies all over the place, the Carnegie Endowment for Peace, the Carnegie Mellon University, all those things, but we are the Carnegie Institute of Washington is our official name, although now we've been rebranded as the Carnegie Institution for Science. We have 6 sister departments. The observatories is one. We also have the Department of Terrestrial Magnetism, Department of Embryology, Global Ecology, Geophysical Labs, Embryology, and I'm probably forgetting one, but you get the point. We're spread all over the United States. There's 3 departments on the West Coast and 3 on the East Coast. Shown here is our headquarters in Washington, D.C. Interestingly, the Carnegie Institution for Science was created as an act of Congress. So that's why we get this really amazing-looking building on P Street in Washington, D.C. And there, of course, is Andrew Carnegie, who got his money through the steel industry, and was probably, by some metrics, the most wealthy individual in American history. It depends on how you do the inflation adjustments and how you count, all that sort of stuff. But definitely gave the most to philanthropic causes. He essentially gave away all his money by the end, which can't be said for most people of his wealth. The other person that really deserves a lot of credit, of course, is George Ellery Hale. For those of you at Caltech or local to Pasadena, you've probably heard his name. So he's responsible for creating the Mount Wilson Solar Observatory. It began as a solar observatory, so the first telescopes up there were to observe the sun. He also had a hand in creating Caltech, the Huntington Library and Botanical Gardens, so he was instrumental in a number of institutions in Pasadena. And why do I say this is the birthplace of astrophysics? Well, there were lots of observatories doing astronomy, making observations. But when Hale created the Carnegie Observatories, he not only brought in astronomers to do the astronomy, he brought in physicists as well. People like Arthur King, Michelson, of Michelson-Morley fame, was here as well. They had a laboratory here, so when you go out and see those big painted circles on our parking lot, the location of the garage used to be a laboratory where they had furnaces, they had giant electromagnets, They were doing the physics. They were putting gases under trying to do the same kind of conditions that you would see in astro objects like a sun or stars. So they were doing the physics as well as the observations, and they were putting these things together to understand the physics of what they were looking at. And as an example, this is Hale here on the right at the SNO Solar Telescope. This here. Anyone seen the movie The Prestige? Yeah? This is Tesla's laboratory in that movie. So I remember seeing the movie and thinking, I know that place. It looks kind of weird. It doesn't look like a telescope. But in this part of the building, there is a celiostat, which takes the light from the sun, directs it down to here, bounces it off, comes up here, bounces it down into a pit, at the bottom of which there is a grating, and then you can see a spectrum. Like this one right here. Now, this is actually not an observation made at the SNO. It was done at the first tower. These are but the prism light from actually comes from the 150 tower. You'll be able to see George Hale was the first to observe Zeeman splitting in the spectrum of sunspots. So he used the Zeeman effect physics plus observations using the tower connection that this was a magnetic field, that solar spots were, or they called them solar vortices back then, were sites of intense magnetic fields. So that was astrophysics being done. And if you're lucky enough to be part of our program, the SNO Solar Telescope, and you can see, oh, that's terrible. And you can kind of tell that there's a... Oh, you know what? We were supposed to put in the ones. Better. So you might be able to see there's a sodium there. You can actually see sodium in the sun directly with your eyes. Now, George Hale is famous for saying, make no little plans, and he certainly followed up on that. Beginning at the Yerkes Observatory with a 40-inch refractor, he then was responsible for the largest telescopes in the world 4 times in a row. So the 40-inch refractor, Mount Wilson 60-inch, Mount Wilson 100-inch, and of course the Palomar 200-inch telescope. And that has big payoffs. If you have the best instruments and you bring the best people to do the best work, you get things like finding the magnetic fields in the sun, determining the size of the Milky Way galaxy. That was Shapley's big contribution. Distances to galaxies, Hubble made that with 100-inch using photographic plates. The expansion of the universe came later when they started putting the Doppler effect into use and figuring out the velocities as well as distances. And of course, there's dark matter in the galaxies from Vera Rubin's work. Those are only just a few. There were lots of other discoveries made. And we have a few videos online of the history of Mount Wilson. So if you're really interested in that kind of thing, let me know and I'll point you to those videos. Of course, this is probably one of the most famous. So I'm just going to take a little bit of time to talk about this one. If you don't know, if you're not familiar with this particular plate, this is our famous bar plate, and it's a picture of the Andromeda Nebula at the time. That's what it was called because, of course, there was a great debate whether this was a object in the galaxy or was it some kind of way. And at the time, they were hunting for novas. And the idea being that, hey, if you can show that there's a lot more novas in this one part of the sky, then that's sort of evidence to say this is a system of its own, with its own novas, because they're happening so often in that one little place. So it was good evidence. But luckily, one of those novas ended up coming back, and then going away, and coming back, and going away. And as you probably know, this ended up being a Cepheid variable, and you probably can't see it. And in fact, if I pulled the plate out right now, and there's a replica in just outside the library, which you can go have a look at, it's very hard to see that Cepheid. And so you immediately know this is the biggest telescope in the world, probably about an hour to an hour and a half exposure, and you can barely see the Cepheid far away. So that settled the debate, of course. And of course, on the right, you've got Hubble looking through the 100-inch during the daytime. But all good things come to an end. This is what Pasadena, actually not even Pasadena, this is what Los Angeles looked like in 1910. Pasadena is actually down here, and you don't even see it. But then by 1925, streetlights become implemented. And it's now, 1925, that Hale and the rest of them decide there's no way the 200 inch is going on Mount Wilson. It's too bright. So that's when it was decided they would have to go somewhere else, which ended up being Palomar Observatory, Mount Palomar. Of course, today, it's even worse. Although, every now and again, when the marine layer is nice and thick, you can almost get back to the way things were. You can see the Milky Way and things like that. But you can't count on that. So, alas, science basically came to an end. If those of you who know George Preston, he's still here. He was the director who pulled the plug on Mount Wilson. And he actually gave us a talk on that. So that's another one I can point you to if you're interested in seeing that kind of thing. So what do you do? Well, if you want to escape light pollution, well, you head to the southern hemisphere because, just look at, or you head out to the middle of nowhere. But it was pretty clear, hey, it's kind of dark down here. So Carnegie decided to go south, and Horace Babcock, the director at the time, initiates a search, and they wanted to go to the south for other reasons too. One is that the center of the Milky Way is almost straight overhead at the right time of year. And also, if you're interested in the large and small Magellanic Clouds, our nearest galactic neighbors, then those are only visible from the southern hemisphere. So again, it's a great place to go. These are images by Yuri Beletsky, who is staff at Las Campanas and who's very famous for making these amazing images at night. In 1968, Las Campanas observatory was purchased for the princely sum of 30 cents an acre. So in current dollars, it cost about $110,000 to buy the observatory. In current dollars, okay, the steel. This is how big the property is. So as you can see, it's a pretty large section of land. And here's what it looks like in 1976. Current instrumentation and telescopes on the mountain. We have our first, which was the Henrietta Swope 40-inch telescope, named after Henrietta Swope, who was an astronomer here, and also was relatively wealthy, her family was, and she bequeathed the money required to build the first telescope down at Las Campanas, and that's why it's named after her. And if it hadn't been for her, probably we would not have gotten going as well as we did. There's a lot of credit for that. And then we have the DuPont, the 100-inch telescope. So it's like taking the 100-inch from up here and putting it down in the south. But of course, its focal ratio is a little different, so it looks a little squatter than the 100-inch. And we have the twin Magellan telescopes, 6.5 meters, that are the largest telescopes we currently have at the facility. And because this is about transients, Las Campanas is pretty famous for a very particular transient, supernova 1997A. So you can probably tell where it is if I go back and forth. You guys are so good at this. This is like, it's like so easy. I won't even bother doing a difference image. So the future, well, here is a view, our latest drone view of the site of the next big telescope at Las Campanas, which is the giant Magellan telescope. And you can actually start to see something that it looks like Stonehenge to me at the moment, but that was an observatory. But it actually starting to look like something round that could actually be there. And of course, what will eventually be there is the GMT. I'm not going to say when. I'm just going to say when it eventually gets made, it will be an amazing instrument to use, an amazing site. Las Campanas isn't at a huge elevation; it's about 8,500 feet. But the skies are very steady, the seeing is very good, and it's very dry, being in the Atacama Desert. Okay, that's all I want to say. So thanks for listening to me, and hope you have a really great meeting. And if you have any questions about anything on campus, let me know, or anybody else that works here. We'd be happy to let you know what you need to know. Thanks.
Thanks very much, Chris. We're running just a little bit behind, but we're going to come up next with Steve Ridgway. He's going to give a talk on the overview of the follow-up ecosystem.
So I should use this for the recording. I interpret my task to be softening you up, to get your guard down for the hard things to come. Oh, I have to find my slides here. So anyone tell me where the slides are? Way. There we go. Yeah, go ahead. Yeah, thanks. Good. You let me know when there's 10 minutes left. Help me gauge the timing. Okay, where are we? Okay, so I'm going to talk about some things that many of you are already familiar with. So I hope that at least you find it not too painful, and maybe even it's interesting. Variable star studies beyond the use of the human eye really started with photographic plates and took off very rapidly when photographic plates were available for astronomy. And the big development in the early part of the century, before the start of the century, was the Harvard sky surveys, north and south, just again and again and again for over 100 years. But not very successful as a quantitative technique. In the field really developed in the early 1950s when photomultipliers adapted into astronomy, and particularly in 1952, Harold Johnson and William Morgan introduced the UBV system, photoelectric system, and if you think about it, they really virtually invented modern astronomy. And I actually remember seeing people observe variable stars like this. The photomultiplier, eye on the eyepiece, chart recorder, measurements were actually in deflections on the chart recorder. You can find that word in the literature. But it led to quantitative data, not at the current state of the art, but awfully good. And with that, variable star astronomy just took off because that's what this was really good at. And just one way of looking at that is what I call the Perryman diagram, after Michael Perryman, who did the first version I saw, which combines a little science and a little art, but gives you an idea of the categorization and sorting that was possible with quantitative measurements. And each of these has had its aficionados. Some have fallen from favor as astronomy has moved somewhat away from stellar astronomy. Some of these objects, most of these objects are periodic, but some are not. They're the transients, and they're very nicely illuminated by this diagram of peak luminosity against characteristic time scale. I call this the Kasliwal diagram after our next speaker. From your PhD thesis, wasn't it? Yeah. And this just illustrates the range of the parameter space. If you're attempting to detect and study rare events which have timescales ranging from 1 day to a year or more, the problem you face in both detecting and adequately characterizing. And to a large extent, that's what this conference is about. Now, what what enabled the kind of survey ecology that we see today. And I'll pick out a couple of technical things and mention a couple of scientific things. Technically, CCD technology developed over about 20 years and rather quickly maxed out at a maximum CCD size. But then what really took off was mosaicing, which was enabled by the development of low-noise, high-speed electronics. So you could actually imagine reading out many CCDs in a reasonable length of time. And, of course, that's where we are continuing to go now. The general computer revolution was very important, and I just picked out here the hard drive capacity as an index. And for your amusement, I put on the relation between the number of gigabytes available on a hard drive, and you see that around 1995, it approached the number of observable stars, and 2005, the number of square arc seconds on the sky. Some interesting numerology. And that was the same time period over which the CCD revolution, mosaic, was taking off. Scientifically, there are a number of things factoring in here. Early in the game, a big one was microlensing searches for machos, which, of course, didn't really go very far as machos are concerned. But it was really developing in the early 90s. And then more recently, and continuing at present, a sustaining motivation, of course, is supernova cosmology. So those are well known. I just pick out here one other, which is pointing out that remind you that the first main sequence exoplanet, main sequence system exoplanet was discovered in 1995. And if you weren't in astronomy at that time, you just may find it hard to understand the impact that had on the science, not on every individual scientist's ongoing activities, but on the context of the public interest in astronomy, NASA focus, decadal survey interest, and exoplanets just took off. And although exoplanets hasn't been a major factor in large surveys, it drove a large number of small surveys, which built up the survey culture enormously during that period. Okay, I'm going to run a little short of time here. So these are major surveys. Started out with the gravitational lensing surveys, and then which detected lots of variable stars. That's what I'm showing here. It's the number of variable targets observed. But we're not generally archived for public use. But that moved in then to larger surveys, which are maintained, curated for public use. And you just point out that this straight line tells me something, to me, astonishing, which is that the number of variable targets available to an astronomer in the public literature, essentially, has doubled every year for 20 years. What other science could say something was even potentially possible? So there are a lot of other sky surveys, in optical sky surveys. Here are some of them. A lot of these are special purpose, smaller, not curated. But I wouldn't count them out as far as the long-term usefulness. I just point out that the Harvard catalog collection of 500,000 some plates is currently being digitized, nearly finished. So this old data may actually be with us for a long time. Surveys and follow-up. Well, I'll just make the point that follow-up is really essential because surveys help to group objects, but they don't generally get into the physics very well. You need to confirm identifications, characterization, so on. And the follow-up is much slower often and has to be applied selectively. And that's part of what we're talking about TOMS for. Okay, so if you want to try to estimate the scope of required follow-up, you look at the big problem. So that's certainly LSST, the LSST mascot. I just want to make a point that of the scope of the LSST project. I mean, in ground-based astronomy, it's just unprecedented. Okay, hundreds of participants, large numbers of institutions, billion-dollar project, 1,000 members of the science collaborations. Okay, there's a lot going on here. How do we get an indication of the follow-up that's required? Well, one guide is the proceedings of the Hot Wiring the Transient Universe meetings, which have been every 2 years approximately since 2007. I'll just skip forward. If you're curious about what hot wiring means, look in the notes. These are very broadly based meetings, mix of science, actual survey reports, follow-up technology, supporting technology. The universal message from these meetings has been, right from the start, prepare now for the data torrent, okay? Thinking specifically of LSST. These warnings started before LSST was, in fact, an approved project. And astronomers are responding, not just you, but by the hundreds. This is a result of a survey. This is a recent one conducted by my observatory. I won't go through the details, but just point out that out of the 400 plus respondents, that there are hundreds interested in queue observing, targets of opportunity with rapid scheduling, time critical, using alert brokers, follow-up observing. So these are hundreds of people out of 400 and some. There are 8,000 members of the American Astronomical Society. I don't know how it scales. It probably doesn't go in proportion, but it's a lot of interest. I'm from the National Observatory, and if I were going to take the time, I'd explain what our response has been. But I'll just sort of cut to the chase and say that among the things that our observatory has initiated in addressing the requirement to provide support for the community in the LSST era, we've initiated a broker project, what you hear about, a data lab project for very large data sets, which you won't hear about, I don't believe. And we joined the EON collaboration, which you will certainly hear about. And just to link into the talks and the sessions following, an ultra-simplified transient follow-up schematic with the surveys provide the discoveries, the alerts. The scientists provide the driving motivations. There's a prioritization process, and all this magic happens in the TOMS, which rationalizes possibly competing, possibly inconsistent, possibly oversubscribed requirements, and makes sensible use of the facilities that are available. Now, speaking of the facilities that are available, let me come back to the National Observatory scene. This is a measure of telescope access, and the measure is in nights per year with the nights multiplied by the aperture in meters. So it's kind of a telescope size weighted. You notice the National Observatory some years back was a dominant source of access to telescopes for the community. And the private facilities were a secondary source. And you can see what's happened in the years since. So the point is, the National Observatory understands a responsibility to provide resources and tools and is approaching that, but the private facilities are going to be an essential component of the follow-up solutions. And again, that ties in with the TOMS because that's access. 1 minute. Okay, where are we here? Yeah, so there's that brings us back to EON, which is this is the reason why the National Observatory is participating in this and will be supporting it best of its ability on into the future. So I'll just read this. The consortium is dedicated to providing the community with access to resources and the tools, and by participating in this workshop, you're contributing to that development, for which we thank you very much. My slides include, and I won't brief them, reference materials, which some of which you'll find useful and some of which you won't find anyplace else. Thank you.
Okay, so before we take the questions, can everyone kind of scoot in and compact a little bit in the center? We have people out in the foyer that haven't had a chance to sit down.
Go ahead.
Okay. I'm going to assume we're good. Okay, do we have any questions for Steve? Well, I have one, actually.
Yeah.
So, relatively recently, SpaceX has had their Starlink launch, and they put 60 satellites in orbit. And they're slated to put thousands of satellites in orbit. And I imagine this is going to play havoc a little bit with big, wide field of view surveys like LSST. Is NAO working with, say, the FCC or something like this to try to control the impact of these global telecommunications networks on?
Right. So, in fact, it's even potentially far worse than you said, because the military is considering launching even larger numbers of low-altitude satellites to support their missions. LSST folks, who are now my colleagues with the reorganization of the observatories, are in fact very interested in that, looking at it closely. The first thing that they tell us is that it's not nearly as bad as it sounds when you take into account solar illumination of satellites or not, and the agreement of the satellite developers to collaborate on reducing visibility. But it's a major issue. Yeah.
Yeah, right. Yeah.
No doubt.
Multiple players in the game.
Yeah.
Right. Any other questions?
If there's nothing else, I'd like to say two things. One is I'd like to endorse Rachel's presentation of a code of conduct for the meeting. I believe very strongly in that. I just remind you that the code of conduct does not just concern bad things you shouldn't do. It concerns good things you should do, one of which is raise all voices, and let's try to make sure that everybody's heard. The second thing is my computer just died, and if somebody could loan me a MacBook power supply, it would help me diagnose the problem. Thank you.
Thank you very much, Steve. Okay, next up we have Manzi Kasliwal, who's going to be talking about the growth Marshal.
All right, good morning. It's a pleasure to be at Carnegie. It's my alma mater. I spent my postdoctoral years right here, so it's lovely to be back. So this morning, what I'd actually like to do is just tell you what happened last night. As some of you may have noticed, we just posted a GCN on the nearest gravitational wave trigger of O3, which was localized to 108 plus minus 40 megaparsec. And last night with ZTF, we searched about a pie of the sky and narrowed it down to 3 candidates. So any of you with the spectrograph, don't listen to my talk. Please get us a spectrum. Okay. So GCN is in your inbox. But let's continue. So what I'm here to tell you about is the growth Marshal. So the first word on that, growth, stands for a National Science Foundation Partnership and International Research and Education Program. The idea behind growth is a longitudinally distributed network of people, even more than observatories. It's quite a heterogeneous network of observatories. But the idea is that when things happen, we have people and telescopes around the world to follow up without waiting for the next night at Palomar. So say we discover something at Palomar, we go around even to the place in the middle of nowhere that we were told exists here in the first talk, and then round the world here to these different telescopes. And growth is growing. We've added 2 more countries since we started. One is LJMU UK, and the other is University of Sydney in Australia. So the idea behind the Growth Marshal, and let me preface this with this is a very small team. My budget was exactly 1 postbac, so which is 1 person who's finished their undergraduate and is doing something before they go on to graduate school for PhD. So it started with this young person, Chris Cannella at Caltech, who's now doing a computer science PhD at Duke. And since Chris moved, Ashod Bagdasarian, another computer science undergraduate, has joined the team and is doing the heavy lifting here. Several other graduate students, postdocs, have assisted, and we've tried to build on the legacy of just our experience as scientists. What do we need to do time domain science here? So let me give you a flavor of what this tool is all about and how it can help with more industry scale versions of this, which is something I hope that Tom will be. This is more the scientist perspective on what do we need to do science right now. So here's a list of design goals. You have the slides. You can read them at your leisure. But the idea here is that even today, even with, even not right now, we don't even have to wait for LSS. Even right now, we're living in an age where there's no dearth of discovery engines putting out hundreds of thousands of alerts, quite literally, 100,000 of the order of 100,000 alerts from ZTF every night. The challenge is how do you design sensible scientific experiments to tackle these large discovery streams, define your science question, figure out which subset of events you really care about and want to follow up and write a paper about. Then how do you corral lots of different follow-up telescopes around the world to actually collect useful scientific data and then convert it to papers and discoveries, right? That's the eventual goal here. So, so if you want to read about this in gory detail, you can look up this PASP paper that the team put together, and it has a flowchart and details about each of the boxes in the flowchart here. I'll just try to give you some pictures. I'd really just like to do a live demo, but this is not my computer, so it's just screenshots. But the idea behind the Growth Marshal, as of yesterday, there were 207 users. So 207 faculty, postdocs, graduate students around the world. And the reason that's important is that it's not just about the 2,600 supernovae, but these 207 users are continuously giving feedback on the system. So we developed it to go live on the day that ZTF alerts started to go out, which is now, I guess, more than a year and a half, nearly 2 years ago now. So these users have contributed to what we call Trello tickets, which is, this is what I need to do for my paper, for my science. This is what the Growth Marshal doesn't do for me right now. So can we add this feature? Can we add this way to analyze the data? There's a continuous input from these users. And that's the idea behind the system, is that it's dynamically evolving every day to add new things that the scientist needs to actually write their papers. So it's become quite a complicated beast here. And many people have adapted to their own science needs as time went along. So this is the front page. And the layout of this page, actually, credit for this goes to Yair Arkavi in the audience here. I think he laid out this Facebook-style page for us when we were developing the IPTF Marshal. So the overall structure of this is inspired by Yair's work many years ago now. But the idea is that this is the home page, and then we'll just work through different aspects of it, right? So these are just different buttons with sub-buttons. This is just a live feed of who's saying what about what source, and it's insane. It's too much. You cannot read all of it. These are the most viewed targets, spectroscopy runs coming up, some managerial things you need to do up here, etc. So let's begin with the TO Marshal. So this is the newest piece of the Growth Marshal. So this is the one that Rachel wanted me to talk a little bit about technologies used. So this is the most advanced as far as coding goes. So this is all based in Flask with celery tasks, etc. All of the credit here goes to Leo Singer, Michael Coughlin, and then graduate students Shreya and Thomas, and postdoc Igor here. So what they do is they continuously are listening to alerts from gravitational waves, neutrinos, Fermi, GRBs, etc. And then they have a list of events with different tags. And then for any given event, there are tools using Michael Coughlin's GWEM optcode, which optimizes how to tile the sky. And here's a random example of how you tile a pie of the sky. And you can actually do this with a camera like ZTF in one night, in a few hours before sunrise. So the idea is you can optimize various parameters here and generate a schedule. And if you press this red go button, then the trigger actually goes to the telescope, and the telescope stops whatever it's doing and starts observing these fields. So step one in this is changing the survey itself. So, the wide field mapping in this case applies to 3 discovery engines: this Wiki Transient Facility, Palomar-Gattini IR, which is a new infrared telescope at Palomar Observatory, and the dark energy camera at CTIO. And all were just in here. So do not press this when you're very sleepy. Okay, and then there's a galaxy targeted optimization for telescopes with smaller fields of view, and that's this tab here, which I won't have time to go into. So regardless of whether there was a gravitational wave alert last night or not, the surveys are generating data, and what we do is we scan for candidates from 3 different discovery engines. So the 3 different discovery engines that we're listening to right now with the Growth Marshal are ZTF, Palomar-Gattini IR, and DECAM. And the way the scanning works is that there are actually, I can't remember now, I think 36 different science programs, each of which is pulling from this very large alert stream in different ways. Somebody in the audience might be most interested in transients that are very red, some in very young transients, some in very blue transients. Pick your flavor, pick your color, pick your age, define your filter, and then dynamically, as the alerts come in, they get cross-matched to these different filters, and you get a list of candidates that you can look at, decide if you like, you want to save to the program, etc. Now, you may decide that this is all too, the language to filter candidates here is too simplistic for you, and you have your own fancy event broker like Antares, Alerts, Lasea. There's an ample service that our German collaborators have developed. So you can say, okay, I don't want to do this step at all within the Growth Marshal framework. Instead, this is a closer look at the same candidates. You can sort of play it up, zoom into different things. But instead, you can add sources directly. So I have a list of sources. I got them ATEL, a GCN, or some fancy event broker output. And you can just say, okay, here's a list of IDs. Let's just ingest by ID through this form into the Marshal. So then by whatever makes sense for your science program, for your particular science that you want to do, you ingest candidates into the Marshal. Now, once you ingest candidates into the Marshal, that's when the fun actually begins here, and you can start to view sources. So some people may recognize an old friend, AT2018 cow. The Growth Network did excellent follow-up. You can see a crazy number of photometry points, a crazy number of spectra here that were taken. But once an event is entered into a particular program, that's when you can trigger a whole host of follow-up, both photometry, spectroscopy, multi-wavelength, whatever your science case demands. You can also start talking about it. I love this source. It's in a beautiful galaxy. Whatever you want to say, something deeper probably is better. That can go here. You can wake people up by pressing the alert buttons. So soft alert is just an email. Hard alert is, call the phone numbers. We do that all the time. Okay, I get woken up a lot, like last night. So that's a useful button. You can cross-match to a whole bunch of databases here. You can decide that this target is, one man's garbage is another man's gold. It looks very interesting, but it's not my science. So in that case, you can transfer this target to another program. Every team almost has built analysis tools. So you can zoom into the light curve. Some people have built light curve fitters to try and see how much does this look like a 1A. In this case, not much really. If you zoom into the spectra, then you can overplot different lines, velocities, fit some things there. Some people are interested in offset from the nucleus of the galaxy. In this case, that's a lot, etc. So various analysis tools are built in here as well. And then some telescopes do fully robotic follow-up. So there are 3 in particular that you press a button and they can do follow-up. And in fact, one of them, the Palomar 60-inch, you don't even press a button. The filter for one of the science programs is so well defined that completely automatically, while everybody's fast asleep, targets come, they pass the filter, and they automatically get scheduled for spectroscopy on the Palomar 60-inch with the SED machine. So we can all sleep blissfully while all of that is happening. So this sort of follow-up coordination can be done for robotic telescopes. In this case, these 300 GITs is, I think, supposed to come online this week. And then there's also an alternate, which is classical request. Somebody has a Keck observing run or a 200-inch or a Notch observing run. So you can do a more classical, I request a spectrum for a particular target type of follow-up coordination. You can make finding charts. You know you need that for a spectrum, getting a spectrum. And if you're at an observing run, then you can get a list of targets, their visibilities, their light curves, some specific criteria. And as you observe them, you can check them off, etc. And then the data from these follow-up telescopes, that photometry and spectroscopy, needs to flow back into the Marshal in as automated a way as the data actually being taken. So you have to close the loop there so that you can update source classifications based on any new information you have in the system. Now, when all the hard work is done of following up things and it's time to write papers, then you try and assemble all of this into tables, right? So here's a snapshot of a random table for a random program where you look at the classification, how many type 1a supernovae do you have, how many type 2s, how many AGN, how many CVs, etc. And then you can do look at different criteria to figure out which ones you actually keep in the sample, don't keep in the sample, etc. And then to really convert this into the table that you want to publish, there are some students who've been developing some additional tools to do that for different programs as well. This also helps keep track of follow-up. So these are different telescopes and the different follow-up assignments. So you can try to balance these and juggle these and stay on top of what spectra you need, what photometry points you need, so that when you eventually write a paper on 1,000 objects, there's some sensible way to wrap your head around all of this. And then finally, since I'm out of time, there's schedules, so you can add things to your calendar, so you can help keep track of them. And there's general information about telescopes, people, programs, etc., that you can access. With that, I'll take questions.
Thank you, Marshal. Do we have any questions?
What fraction of the Palomar 60-inch time is used for follow-up?
So I hope I get these numbers right, Matthew, but I think 70% of the time is, two-thirds, 66% to be precise, is reserved for ZTF follow-up, and 1/3 is assigned by the Caltech DAC for these programs, so any for all the ZTF programs. It's a majority.
Okay.
So how much of the growth Marshal is based on the PTF Marshal? Like, because as you said, you had a really big, a good starting place there. So how much of that is new versus how much of that is old code?
Yeah, no, that's a great question. So we tried to keep some elements that people are familiar with, like the architecture of the front page, and some of the tools that people were used to and familiar, but we rewrote it because it was just not scalable the way the PTF, IPTF framework was written. There was no way to actually scan for candidates in that, listen to different discovery engines, keep up with this idea that there are many different science programs, many different people doing different types of things. And then we have this thing now called automated annotations where people can develop their own analysis tools. So say you decide that a metric on the light curve is very important for your science program. So you can write a little piece of code that automatically adds that to all your targets in the science program, and then you can filter and choose by that. So wherever we could, we try to recycle and reuse, right? So it helps the user base if things are familiar. But Chris really had to start from a fresh plate to build a system that's scalable and survivable in the ZTF era. But that said, this is something that we needed on day one for ZTF. That's what we had a hard deadline for that, and one resource. So there are many, many things that, at least from a computer science point of view, architecturally could be done much, much better. And I sincerely hope that the lessons that people will take away from the Growth Marshal when developing something like TOM are the science use cases, all the science applications, because that's the strength of this system, is that because 200 people have used this for so many years, there's a lot of feedback in it on what scientists need to write papers. So that feature set is really, I think, what new tools that are being developed for LSST should take away and use from this.
Another question?
The other question I had was just real quick: is it open source?
The growth TO Marshal, which is the newest one, is you just GitHub and it's there. The rest of it is not. You have to be friends with us.
I actually have a question. So I thought that was a beautiful page that showed like the gravitational wave details and your observation plans. Do you also change your observation strategy? So you mentioned that was the closest trigger, so you're maybe taking smaller exposures, or if you have component masses or something, maybe you're searching for a model. Do you
Absolutely.
do okay.
Yeah, we have to change on the fly. So we change exposure times, the area we want to cover, filters, cadence, even things like, CTF is serendipitously going to cover this piece of the sky, so we'll go and enhance it by covering this piece of the sky, etc.
Right.
Or some other telescope in the growth network is going to cover the northern celestial poles, we'll do the rest, etc. There's a lot of dynamic. I mean, you can just take the default plan and press go if you're super sleepy, but usually you do a little bit more optimization.
Thank you. All right, and I think that's it. Next up, we'll have Rachel. And she will talk about the science motivation for the TOM Toolkit.
Oh, thank you. Yeah, no. There we go. Okay, so I wanted to start by giving a quick introduction about why we built the toolkit in the first place and the overall science motivation for it. And before I begin, I want to highlight that this has been a real collaboration between the software teams at LCO and our in-house science teams who have provided a lot of advice. So we all know that the managing of astronomical observing programs is getting more complicated. We have more extensive target lists being developed and distributed faster than ever before. A lot of us don't know what our targets are going to be in advance. Ask Nancy, she got a new one in last night. We have new rapid alerts and we have the capability to respond to those alerts far more rapidly than ever before. And we find ourselves coordinating these observations across a wide range of resources. This produces a great deal of data products which have to be then managed. So the idea of having software tools to do that management process is not a new one. In fact, it goes back more than a decade. And the way that this has really come to light for us at LCO was that we found our own programs developing such tools in order to achieve our own science. So to give you a little bit of the background, I thought I'd give you a very quick overview of some of the tools we've developed for our own science prior to the toolkit to being produced. One of the earliest programs that we started to do was the microlensing program at LCO. This began back in 2007. And this is an entirely automated workflow. In fact, contrary to other different areas of science, we found that when our users got involved, they actually screwed it up. So we took the buttons away from them, and we allow them to observe entirely automatically. The computer receives targets automatically, chooses what to observe and how to do it, and sends us the data afterwards. On the flip side of the coin, other astronomers have a very different workflow. The SNEX transient TOM system, which you can see a screenshot of in the slide here, began development in 2013, but their workflow necessitated quite a different approach. They have an extremely sophisticated UI, which Jamie and Curtis will tell you more about later. And obviously, their science use case was very different, so it had to integrate with some very different software for the data reduction, the archive, the pipeline development, and so on. But there's a lot of common tools. You'll notice they plot light curves, so do we. They schedule observations, so do we. We also have a solar system group at LCO, and their TOM system is customized for the nature of their targets, which of course has a set of different parameters that I don't care about. My targets don't move, at least not the way they do. So their background Tom, they have a very similar storage system, but their visualization tools are quite different. Their data input tools are quite different, and the way they share data is quite different. And in the emphasis of open source, I personally feel very strongly about this, so I wanted to point out that all of these Tom systems are open source. You can have a look at the GitHub repos. They're actually based on Django, very similar to the Tom toolkit, so you can see where it came from and take a look at some of those tools. When we took a look at those tools and we all compared notes, we discovered that there was a great deal of common functionality. Now, obviously, we have very different science use cases. We all have very different sets of parameters, different data sets, and different science goals. But there's a lot of common storage areas. And it was really, we decided that we were basically reinventing the wheel a lot of the time. And we were all scientists writing code, and we're not software engineers by training. So we decided it would be better to have a software team do the common core functionality. So we looked at what the requirements would be. We all have more targets than we have ever had before, and the situation's getting worse. We have a common set of target brokers. They're usually fairly large programs and data catalogs that are serving those. And we all need to talk to the same brokers and catalogs. But we have to have science-specific software that allows us to select the targets that are interested to us personally and prioritize them according to our own decision-making. Our observing strategy is often a function of time. We always have new alerts coming in. We also have existing targets of interest that we need to continue to follow over a period of time. And what we observe at any given time can change depending on the behavior of the target. Of course, to make these observations, for the large part, we are all using common user facilities. So we are interacting with the same set of facilities, leading to the same interfaces being used. Sandy, is it sharing? Okay. Curtis, could you help out there, please? Thank you. So we all end up coordinating observations from multiple different facilities. This slide gives you a classic example of a transit planet candidate and the types of different observations that you need to take. Now, we can all think of our own examples in our own science areas, but in this case, you need time series photometry, spectroscopy, and AO imaging, just to give an example, and all of those things are conducted by different telescopes. We tend to think of surveys as producing the big data in astronomy, and of course that is true. But I wanted to point out that dealing with a follow-up program can be non-trivial. A typical key project at LCO took, for a duration of 3 years, took upwards of 15,000 individual data files, well over 2,500 observations, and 4 terabytes of data products. And in order to store those, you need to have them in a searchable, accessible format and display them in a meaningful way. Otherwise, you have a data curation problem you can't keep track of. We also have distributed teams, as many of the existing TOMs will illustrate. We have large collaborations, often international, and we all have to be able to access the same data displays in order to coordinate what we're doing. However, as any of the TOM developers will tell you, and I'm sure Yair will back me up at this point, developing one of these systems is non-trivial if you do it from scratch. There's an enormous amount of effort that goes into writing this software, and even adapting existing code was problematic. It was a lot of investment of time and effort. And it involves a lot of databasing skills which most astronomers don't get training in. And so our motivation for developing the TOM toolkit was to build an open source package which was available to everybody, developed by professional software engineers, but designed in such a way that it would enable astronomers to easily build software systems that they could then customize for their own science code, their own science use. It was to provide a core set of functions for those commonly used components to stop us all reinventing the wheel, and a set of well-defined interfaces so that we can plug our own code into the TOM and get it to do the kind of analysis that we want to do, the kind of science that is distinctive to our project. And last but not by no means least is the fourth bullet point on that page is to build a community of TOM users, because in the open source software model, there's a great deal of sharing between users, and it's an extremely powerful way of crowdsourcing development and making the package stronger. And that's why all you guys are here. And on to the next phase of the development program. We have, as you know, the call for proposals. So you should all have received an email about the call for proposals. It went out about 3 weeks ago. You can find more information on the meeting website, but I'm just going to run through a few of the details. The important one, of course, is when do you submit it? It's about a week after this workshop finishes, so don't forget. Note that that's in my time zone, so the resources available are up to 1,000 hours on the Las Cumbres 1-meter telescope network. You can ask for any instrument and in any scheduling mode, so that's standard queue mode, rapid response, or a specific time-critical window. Thanks to our partners at the SOAR telescope, we have 50 hours of time available on that on that telescope as well. Again, you can request any instrument and any scheduling mode, but I will point out that the SOAR telescope has recently become programmatically available thanks to its partnership and excellent work by their team to bring it online in the AON network. So queue scheduling is preferred if that is suitable for your program. Say again? So we can talk about this in a bit. Perhaps, Stacey, you'd like to answer that question?
No, sorry, it's not for a while. But it can be accessed. About 80% of
We also have 50 hours available on both Gemini North and Gemini South. In this case, queue mode observing is preferred, but other modes are available. There is a comprehensive list of the instruments for which time that is available on the website. And I wanted to point out that we are lucky to have Brian Miller here, who can also advise from Gemini. The observing programs that you proposed for should start in December this year and end December next year. The Time Allocation Committee will arrange to have the time requested distributed fairly evenly across semesters A and B. We encourage proposals that request a combination of facilities, and you're welcome to include facilities that you have access to in addition to the ones on offer through this proposal channel. In addition to the telescope time, you may also request for grants for up to $45,000 in US. These will be paid to a single recipient. I'm afraid we can't distribute it across organizations. That's up to you. But you can include anything from equipment, publication charges, services such as cloud hosting fees, etc. In terms of the proposal specifics, I strongly recommend you use the LaTeX template provided. The page limits are maxima. Don't feel you have to do 10-page proposals. Feel free to do them smaller and concise if you can, but do be aware to use anonymized language wherever possible. Be specific about your technical detail. It will enormously help the observatory staff to evaluate the practicalities of your proposal. And the submission is quite simple. You just email it to me at that address. The reason that we ask you to use anonymized language is that anonymization has been demonstrated to be an extremely effective way of making astronomy more accessible for all communities in astronomy. So we are asking you to constrain the identities of the people proposing to the first page. This will be stripped off the proposals before they go to the TAC, so the TAC will not know who they are evaluating. The TAC will be composed of a selection of SOC members and observatory representatives for the technical advice, as well as some invited domain experts, so that we make sure that we have experts in all of the science areas covered. You can expect results by November 15th this year, so in good time for you to set up your observing programs. A successful proposal, we will ask you to report back at the end of your program. We will look for a report describing your results and the data you have produced as a result. This will include software projects. I know a lot of people, traditionally, these have not been, in my opinion, adequately recognized. So just to point out that we do recognize that as a very valid product of your proposals. We will also value community contributions. So we strongly encourage collaborations. And I'd encourage all of you to be open to new team members that you meet here at the workshop. We've deliberately invited a wide selection of the community work together. And I hope that the successful teams will really contribute to a user-shared resource community. And that's it from me. I'm happy to answer any questions that you have on the proposal process or on the Toolkit.
Hi. So, what is the relationship between the proposal process and the TOM toolkit? Like, do you need to use the TOM toolkit in the science program that you propose, or, you know?
Highly recommended. That's why you're here.
Yeah. So, okay. So, so it's strongly encouraged.
Strongly encouraged.
Okay. Thank you.
I'm going to make you run for your living. I'm sorry.
In regards to the software projects, are you thinking things like, I don't know, TOMs for telescopes that aren't yet inside Aeon
or you can imagine
else?
making plugins, for example.
I don't know what that means.
So a tool that's designed to fit within the framework of the toolkit or interact with, say, a common service. We're obviously providing a set of interfaces for very common facilities, but we'd love to grow that. But we really need feedback from you guys, the users, to know what is most important to you, what services would you like to be able to talk to and interface with. So getting that feedback from you we see that as a very important element of this process. So you could imagine teams, for example, building an interface for a telescope that we haven't yet considered, or a data archive that we haven't yet interfaced with. And that would be a very useful product. Okay.
You said that the maximum number of pages is like a hard limit.
The maximum number, yes.
Yeah, but you were kind of more soft on the timescale. You said the proposals are due in about a week. Is it about a week? Is it exactly a week?
I did have
it's fall break next
the
week.
exact deadline is up there. It's October the 13th. At 1 minute to midnight my time.
You sure?
I'm sure about that bit, yes.
Most astronomers work in UT, right?
Sorry?
We work in UT normally.
Yeah, well, that is true, but as far as I'm concerned, it's PDT.
Hello. A bit fundamental question I still have about the purpose of the project, which is if at the end of the day, you want, for example, one toolkit specifically designed, for example, for, let's say, SOAR telescope, and the whole community who contribute or not contributed to it will use that, or if you, in the end, will encourage different teams to use different version, their own customized version of the toolkit to trigger the same telescope.
So the toolkit, you can think of it as a package or a library, very much like AstroPi. So you can install it and use it to build a TOM system for your own purpose. You can push code upstream back to the toolkit and contribute, say, a plugin or a specific tool. But you use it to build your own system, which is customized for your purpose.
One team can trigger Gemini. Another team cannot.
We actually have a plugin for Gemini already, so let's say somebody builds a plugin for Keck, which we don't currently support. That would be great, by the way, just throwing it out there as an idea. So suppose somebody, as a result of this, goes away and builds a plugin that can do that, that's great. They have it in their own TOM system, wonderful. We will be talking on Friday about how you can contribute that back upstream. You as a user, if you write some code you think would be useful for the rest of the community, we will provide a mechanism for you to be able to say, hey, I've done something useful. Can we integrate that with a cool toolkit? And we'll we'll have a way to bring that in so that you can then share it with the rest of the community. And then everyone can use it. Okay. I think Melissa had a question.
I had a question about the collaborations being strongly encouraged and the role of this meeting in fostering collaboration. And I couldn't tell from the schedule whether we're going to be doing pitches to find like-minded people who want to write a proposal with us, if some of the breakout sessions are devoted to working on the proposals, or if we're doing other things, or like what are we doing with respect to proposals?
We have several discussion periods in the schedule, and you should absolutely consider those times for you to pitch your own ideas. We would love to hear ideas, and if one of them is, hey, let's spend half an hour getting our heads together and brainstorming ideas, fantastic. Propose it and we'll make sure that happens.
Okay, so there's pitch and working sessions later
Yes,
this meeting?
yes.
Oh.
One of them is later on today. So who's up next? I think Yaya was first and then Dimitri.
So is this working?
It's not broadcasting sound.
Sorry,
so
okay.
Let me explain, actually. That is capturing sound for the Blue Jeans channel. But we don't have any speakers in the room, so you're not going to hear yourself amplified.
Okay, good. So you mentioned some of the goals of the TOM Toolkit. You mentioned motivation that we're not computer programmers, so we need the professionals to do the infrastructure part for us. But another goal was powerful interfaces. I think you had it. We even less than computer programmers, we are even less so user experience designers. So usually things built by astronomers are not the easiest or most intuitive things to use, and I think that's an important aspect. Now that we are building tools for communities for hundreds of people to use, is there any person or guidance in the TOM Toolkit about also good design practices, and not just what it does under the hood, but how it is experienced by the user in the front end?
We will have a session covering the building of views and interactive forms. Does one of the software team want to speak to the good practices in terms of designing user interfaces?
Well, the answer is no, we don't have it yet.
Okay, yeah, because I mean, UX is a profession now. It's not just like a nice-to-have thing, and so it would be good to have an expert in recognizing that, astronomers are usually terrible at this, to help us out with that.
It is one area where I think this sort of workshop is really important, because we have some really excellent software developers involved in this program, but only really the scientists can tell us how you want to use it, and every single person here has a different idea of what a good UX actually is. So that's partly why this workshop is a good place to start. I think you have one more question. I think we probably have to move on.
Just to make sure I understand this correctly, so the proposals don't have to be technical plus scientific. It could be just technical, so I want to write this piece of software, or mostly scientific, like I want to do this kind of science and use the TOM Toolkit for that.
We envision that most astronomers would be interested in running an observing program, but if you have a specific science or scientifically themed software to develop that you think would be useful for the community at large, then sure, propose it by all means.
Thanks.
Sandy at the back.
I think I heard someone ask, what if two teams propose the same plugin? Like, what if two teams wanted to do a Keck plugin, but perhaps the breakout sessions would prevent that from happening?
Coordinating in the breakout sessions is a great way to avoid that happening, yes. I would start there. We don't preclude if two teams absolutely adamantly want to propose exactly the same thing separately. They're welcome to do so, and the TAC will sort it out.
Okay. Thank you very much, Rachel. So the next session we have is with Jameson Burke and Curtis McCulley talking about snacks today.
we have a double act. Who gets the microphone first?
First, I think these guys.
You can do it as a coordinator. One person controls it. One person.
All right. Well, so first of all, thank you very much for all coming to this. This is very exciting to me personally because this lives at the intersection between software and science, which is a real passion of mine. So today I'm going to tell you a little bit about our journey in the supernova group at the Las Cumbres Observatory. So this is building on a lot of work that Yair did, and it started kind of actually with what Muncie said, that it started as the PTF, and then it got, it's evolved over time. And so this is kind of the next stage in the evolution of this project. So as Rachel showed before, we have this thing called the Supernova Exchange. This is designed basically entirely by Yair Arkavi. And even though he pretends he's not an expert in UX, it's one of the best UX experiences I have. I think it's also safe to say maybe the Growth Marshal is now comparable, but it's one of the most sophisticated TOM systems in existence. That's certainly true. It's become really, really indispensable for our workflow. So at any given time, we're following 50 supernovae or so, and we have hundreds of supernovae in our database. Now, keeping track of that with just a couple of grad students and a postdoc, it is going to be really, really difficult without a system like this. So let's see if I can get this to work. So this is just a little demo we put together. This is the front page, very Google-esque, very minimalist. There's some design principle here, I think, Yair. What do you think? You would know. So the idea is on the front page, you can say put in a target and start looking for it. So this is a particular 1A that's in our system, and we let it load. And it's basically very much like the Growth Marshal. We have, a Facebook page for all of our targets now. We have comments. We have our latest images. The observability would be there if it was actually observable, which it's not at the moment. So that the particular right panel is blank. It's got what are we interested in scientifically on the left side. Who is interested? Yeah. Rachel. Is somebody running the slides back there? Okay. Okay. Okay, cool. Great. Well, I have no idea what's going on there, though. Again, all these plots are interactive. As Rachel said, we have a lot of things very similar. We're plotting light curves. We're plotting spectra. We have this line plotting interface, so we can go look at individual spectra. And so hopefully the video will scroll down shortly. And so these are our individual spectra on the supernova. Now we can do some basic analysis in line, like saying, okay, this is a 1A, so what's the silicon velocity, for example? And so you can do basic velocity measurements, and it's become really an invaluable tool. How many users do we have now, Yair? Do you know? 200? A couple hundred, 200 roughly at this point. So again, this is another very widely used system, and it's become really invaluable to the supernova group's work at Las Cumbres especially. Oh, and then the last thing I'm going to show in this video is this is our scheduling page. So this is how we manage our follow-up. We have sequences of all of our live supernovae in line, and so an hour a day or so, 3 or 4 people can manage an entire collaboration of 100 to 200 people, and all the follow-up that goes along with it. So these are different light curves of different objects. Some are in better shape than others. This is all automatically produced, automatically ingested. All the data you're seeing here went from telescope to an archive into our system with no human interaction. So there's a lot of really great things about this. I mean, the UX is fantastic. Just the supernova group could not function without this at this point. It's become completely irreplaceable. this allows full international collaboration. We have a URL that's accessible to anyone around the world, and so people are using it. Yair is mostly in Israel now, and so he's using it on the other side of the world. It's been very well battle tested. It works quite well. The hard part is Yair has now become like some fancy faculty in Tel Aviv, and he's off, getting grants and like making us all look bad. And I think this is a common story. You have something that's a single person has built, and it's grown over time, right? We didn't really know the full direction we needed to go when we started. It really kind of grew organically, and over time, the project got pretty big. So it's almost 1 million lines of code at this point. Yeah.
I can show you the command that got that number.
A very, very large fraction of that was written by you. And there's there's a lot of interesting. I mean, that's a very big rabbit hole that we could go down. But the things that has happened is it's become a little bit unwieldy to maintain. Yair is now doing other things, and it's like, okay, here you go, Curtis. Here, like, good luck. And then, so we've really come into the situation where we need something that both scales with the size of the data we're getting, but it's something that somebody who wasn't deeply involved in writing the original project can maintain. So future grad students can come along and say, oh yeah, sure, I can add this new plugin. It's got some other things like it's starting to just feel its age in some respects. It was Python 2, which was totally reasonable in 2013. Now Python 3 is the thing, and so we have to do that. There's a lot of very custom HTML and JavaScript, and so there are places where if there's one thing we need to change about all the pages, we have to make that change in many, many places. And so we really wanted something that was going to be something not only we could use that was battle tested like this, but something that we could maintain. And so there's kind of this change in philosophy on what we're going to do. And Jamie says he still doesn't even actually know how it works, and so that's a different problem.
Okay, so I'm going to take over now. So I've been making SNEX 2.0 using the Tom Toolkit. So the next slide will just be a video walkthrough of where it's at now. People who are at Hotwired, some of this will look familiar, but some big changes since then. So this is the homepage for SNEX 2. It's at test.supernova.exchange. It's got the latest comments, latest targets that have been added. This is what it looks like now. You'll be making your own Tom later today, so you'll see what it looks like. Here's the targets page. I've ingested all the targets that were in SNEX, so there's 3,500 supernovae and assorted transients. There's a map of them, and you can filter that down. So if we only want to look at type 1a supernovae, here are 673 type 1a supernovae. Here's a map of them. You can zoom in and scroll around. See their names and stuff. Also see the galactic plane in there, so that's cool. So a big part of the Tom toolkit is being able to interface with these alert brokers. So here's a query that I wrote that queries Mars, which is the Luskin race ZTF alert broker. So you can query by time or location or brightness. So I've cherry-picked a few to get some interesting targets. And also by the real bogus factor. So let's run that alert, and then it'll return a list of targets that satisfied that. So I happen to know one is very interesting. So we can go look at that one on Mars. And there is what its light curve looks like. So that looks like an interesting target that I would want in my Tom. So I can create a target page from that. And when I do that, it takes it over to this page, which is the generic page for creating a target, so I can add different names to it. We recently added the ability to add an arbitrary number of aliases for any target, because astronomers love naming things, so you can have as many names as you want for each target. We create that page, and this is what the target page looks like. So again, each target has its own kind of Facebook-style page. This is what it looks like in the Tom Toolkit. You can see it automatically ingested the photometry from ZTF down there. And that plot's interactive, so if you only want to look at one filter or scroll in, you can do whatever you want there. Some details for it up there. You can write comments on it. You can look at the survey view of what galaxy it's in. That's a plot of the air mass at LCO sites, so you can assess whether or not you want to observe it, whether or not it's a good target. Okay, cool. So you can also schedule observations through the TOM. So here's the form for scheduling at Las Cumbres, which I've customized a lot from the default that's in the TOM toolkit. You can pick what proposal you want to submit your observations through, what exposure times you want. I'm going to submit, and then it says, oh no, you can't do that. That's because we have automated form validation, and that proposal doesn't have time on those telescopes. So, cool. Give up, or what about, it's getting kind of faint, so like, I don't want to observe it on a 1 meter telescope. What if I want to observe it on an 8 meter telescope? So this is something I've added recently. So people who observed on Gemini, this should look familiar. This is the Gemini OT, phase 2 OT for submitting observations. I've used this several times, and every time I use it, I get really nervous that I'm going to like forget to input a certain field, and I'm going to like waste thousands of dollars in telescope time and stuff. So there's this module that was contributed by Brian Miller. So thank you so much for your work, and I also changed it significantly. So, you can schedule an observation on Gemini for your TOM. So once in the next 2 days at that air mass. With these filters and exposure times, limit the number of exposure times you can select because I don't want people to do anything dumb. And I'm going to submit that observation. Okay, and then it's going to load. It's going to interface with the Gemini database. Okay, it submitted the observation. And then when I go back down to the OT and reload it, then it's there. Like magic. So currently I have only developed it for optical imaging because that was the easiest thing for me to do. But you can see it copied over the exposure times that you wanted and the air masses. So currently it's for GMOS, although it works by copying the templates that you have. So it could be for whatever templates you have set up.
Brian Miller can say more about that.
And yeah,
in general, will handle any Gemini.
Right.
This has been modified.
Right.
This goes does either
Yes, and so currently when it submits the observations, it puts them on hold, and this is also a test OT, so I haven't actually tried to trigger Gemini through it yet. Full disclosure, it's a couple steps removed, but that is the plan in the future for Villanova follow-up or something. Great to not have to download the OT. You could do it from your phone if you wanted to, which would be sick. So this is another thing that I've this is a targets that are on the TNS. And so for this page, it has a list of targets on the TNS and then a plot of what the survey view looks like and whether they're visible at LCO, when their last non-detection was, and what their recent photometry is. And you can filter, so you can look at targets that were discovered by Atlas that are bright enough to do spectroscopy at Las Cumbres with, where their last non-detection was in the last X number of days. Last non-detection is a super useful thing for being able to find young, interesting targets, but the TNS makes it very frustratingly difficult to get that information. So I wanted to make it easier, which is what I did. So you input that and it returns a few very interesting, potentially interesting targets. So that was like 20th magnitude 5 days ago. Now it's 18th magnitude. And it's probably associated with that galaxy. So potentially interesting target to add to my TOM. And that page is not in the base toolkit at all. Just something that I totally added by myself. But the TOM toolkit is designed for you to extend it however your science needs it. So for people who are interested in SNEX2, currently it's private because we ingested a lot of proprietary data, but I made a public version of it. Few, like 4 or 5 targets. It's called millisnacks. It only has 4 targets instead of 4,000, and I'm very creative. So if you want to go on there and like poke around a TOM that has data in it, you can go to this website. Heroku is this thing we're going to discuss later in the workshop. It's a way to deploy your TOMs for free, so that's very convenient. You will need to log in, but I did put the credentials on the home page. It's millisnacks, and the password is melon, which you might remember is Elvish for friend. Okay, so another point is that TOMs are very customizable. So this is a version of Snex 2 where I like lazily, I don't know any HTML or CSS, and I just like lazily tried to make it look sort of like Snex. So everything's kind of in the place where Snex is, although it's missing a lot of features that we don't have yet. So you can reorganize the page however you want. It's up to you. So just some comparison here. So like we said, old Snex, the code base is extremely large. I promise it is. Yair. New Snex is much smaller. So instead of like 1 million lines of code, it's like 2,000. So I'd say that's an improvement. It's all also open source. It's on GitHub. If there was any part of this that you were like, man, I really wish my TOM looked like that or had that functionality, you can just go to the GitHub, copy it. That's what it's for. So some pros and cons. We're all here to build TOMs, but just to give you some thoughts. The TOM toolkit's great because new TOM like literally in 30 seconds. Super easy. It's also very easy to test it, right? You can run a local server. You can make changes there and see what that does before you push the changes to your development or to your. There's also a lot of documentation, both TOM documentation written mostly by Austin and David, and also general Django documentation, which is very helpful for solving any problems you encounter. And then also the projects it makes are very manageable, so it's super useful. There are some cons. It automatically makes a database for you, which is extremely useful because as astronomers, we don't always know how to make databases well. But then that can make it hard to interface with existing databases. So that's definitely been a pain point. We are still working on the UX for it, of course. And there are some key features that we'll need to add before Snex 2 becomes. So that's where we're at now. Thank you. And if you have any questions, we'll take them. Here are our contacts.
So you said your plots are interactive. So you can actually, on the spectra, for example, you can sort of zoom around and zoom in a particular region of the spectrum and so on. And also, any of the plots that you have there, you can easily print out, save to a PDF or whatever. Any of the plots that you have, the spectral light curves, the visibility chart, all of them have printing plugins or oh, okay.
Yeah. So again, if you do want to like look around a public version, I'd encourage you to go to that URL. You can see what the plots actually feel like if you want to interact with them.
Yeah, I think you might have to enable the print. Like you just want the plot. But that's just something we haven't enabled by default.
So you guys built this on the TOM toolkit?
Yeah, that's correct. Yeah.
Okay. So in principle, anyone could recreate this with import TOM toolkit.
Yep. If you
lay down a bunch of elements, and then you have something that's more.
Yeah. If you clone the GitHub and then add an API key and run manage.py run server, then yeah.
That's pretty
and
cool.
That's what Griffin did at Hotwired. And yeah, I don't know if you want to speak to.
And this was a good opportunity to really interface with the TOM toolkit and make sure that we are testing how to use it. And then it gives us the added benefit if we have something.
Can you talk more to working with existing databases instead of SQLite?
Yes, absolutely. So I imported all of the targets into SNEX2, I think back in May, it was a while ago. And then just in the last week, there's been a significant change to the Tom Toolkit database. It added the ability to have an arbitrary number of aliases for each target. And so I have not tried to like re-import or keep them live, but Curtis and I do have a plan for that, so he can talk more about how that'll actually work.
Yeah, we can talk about databases in a lot more detail if you'd like, probably later. But kind of the short of it is we wanted to use this as an opportunity to take advantage of the models that are in the Tom Toolkit. And so we basically wrote an adapter to convert the data from our old database into our new database. Running it and saying like, oh, I just want to keep this database running it by itself is still not trivial. And so, no. So the beauty about Django is it's an ORM, and so actually it can be, it can be Postgres, it can be SQLite, it can be whatever. So, so you're not locked into SQLite at all.
And yeah, the current SNEX2 database is Postgres.
Yeah.
But you're having to write your own extract. And if there's like schema that you've implemented that is just germane to your own stuff, you're saying running that schema side by side with this Django project is complicated.
I think that's something we're still developing. Yeah. If it's just purely additive, it's not very difficult to add a new model to your Tom. It's if you represent your targets in a significant than Tom base does, there's some overlap. But if you want to just add a new feature, that's really
Does this system include any kind of data analysis or reductions of the actual pixels, or are these just data ingested from other places that have already been done in some way and you're just plotting them?
So right now there's no way. Right now on SNEX2 there's no way to like run a pipeline, but Austin, I'm talking about the education Tom. You might know more about that.
There's definitely, we have the concept of being able to run arbitrary code on data products. So it's definitely possible to do whatever kind of analytics you want. But we don't really have any out-of-the-box pipelines included in the toolkit at the moment.
So all the data we have on SNEX was reduced at the pixel level. So almost all of this data was images. Not by SNEX. We have a separate pipeline which is then integrated with SNEX. So it's not. They're basically run in parallel.
I have another question. So, as a content management platform, SNEX, right? It's a Django project. Do you have the ability to do any like direct SQL ad hoc querying? Say, like I want to say, come up with some arbitrary predicate and pull out, supernova IDs or whatever. Is there a way to do that? I know Django has plugins like SQL Explorer, et cetera.
Yeah, so you can go into the direct SQL. I very strongly recommend using the ORM though, and that because then you can do all these queries, but they're treated like Python objects, and then they're completely database agnostic. So you can run SQLite, you can run Postgres, or anything like that, and they're also a little bit easier to read often, and able to do some of the optimizations of the actual raw SQL under the hood. You can just call raw SQL. That is a possibility. It's just not what my recommendation would be.
Could you talk a little bit about why you decided to use Django instead of maybe some more lightweight solutions that are out there, like Blast plus SQL Alchemy has an ORM. There's Tornado. There are other things that are sort of. Django has kind of a reputation as being this behemoth thing that is very hard to, for your average user to just kind of learn it because it's so, it's so big and has so many features that it's great for, stuff like, I don't know, like big companies' websites that are very complicated and have a lot of moving pieces. But for astronomers, it might be a little bit overkill. So I just wonder, like, what's the thought process there?
So Django is a batteries included approach to web development, yet this framework is taking advantage of pretty much every feature that it has. So, for example, user management, the database ORM, templating engine, that's all stuff that comes with Django. That's not something you get with a lighter weight framework. So if we were to build the toolkit with a lighter weight framework, we would have to make some kind of hodgepodge, all that stuff anyways. So the advantage of using something like Django is that it is opinionated and it all works together. Okay? If we use something like Flask, it would be a mess.
I think in answer to that question as well, it's worth pointing out that there were existing TOM systems that were also built with Django and made full use of its functionality prior to the development of the TOM toolkit. So it was a natural evolution.
There's nothing in here I can do with a different tools.
Okay, and if there's any other questions? No? Okay. Let's thank our speakers and thank everyone that spoke at the session. And it's coffee time, I believe. So.